Now, in earlier part of this probably chapter, we talked about how to use tree diagram to help us to do the counting. Okay, so this is one example. Okay, flip a coin and spin this wheel. Okay, we're going to figure out for this whole experiment how many possible situations. Now we know that flipping coin there are 2 situations, and then you spin this wheel there are 4 situations. Right? So totally how many possible outcomes? There are 8 possible outcomes. Okay, so because 2 outcomes here, and after each of those outcomes there are 4 possible situations. Right? So you have 2 outcomes here, and you have 4 outcomes here. 2 times 4, you get the 8 possible outcomes. That's what we mentioned last time. What is the basic principle of counting? Right? Sometimes we call it fundamental principle of counting. Okay, and so we can list all the possible outcomes in a sample space. A lot of time when you do probability problem to try to calculate probability for certain event under the assumption of equally likely outcomes. Okay, then if we know how to count how many possible outcomes in the sample space and also number of possible outcomes in the event, then use that ratio, we get the probability, right? But how do we figure out how many possible outcomes are there? Now that's what we're going to talk about today. Okay, this is another example. Talk about casting 2 dice. Okay, how many possible outcomes? There are 36. Again, we can use a tree diagram to help us figure that out. But if you use a principle of counting, there are 2 steps, right? First step is casting first die. There are 6 possible situations, right? And then casting second die, there are 6 possible situations. So 6 times 6, we get totally 36 possible outcomes. You can list them all. And you also see this diagram there. This is like a list of all the sample space, all the possible situations. So if I ask you what's the chance of getting that outcome that the sum of the 2 dice is 7, then I figured out that, well, all these outcomes in the diagonal, that sum is 7. Right? There are 6 of them, 6 out of 36. So we know the chance of getting that sum is equal to 7 is what? 6 over 36, or say 1/6. Okay? What's the chance of both of them are 6? That's just this 1 out of all the 36 outcomes. So the chance of getting 2 6s is 1 over 36. Okay? And we also learned that independence of event. We know that there is another way to solve that problem, right? 2 events are independent, and the chance of getting a 6 is 1/6. Chance of getting another 6 is 1/6. 1/6 times 1/6 is 1/36. We did that too, right? So this is just to tell you that there are several ways, in many situations, there are several approaches to solve a problem. Okay, whichever way that you feel that is more efficient to solve the problem, probably you would take that. Okay, in order to solve the problem faster. Okay. Now that's the tree diagram I mentioned earlier, and then. This is what we did last time. We talked about what is the counting rule. Basically just developed based on that tree diagram, right? If you have a very clear idea about that tree diagram, and this is actually the result, you get this kind of rule or counting rule. If you have an experiment that involves several steps, okay, each steps have different number of outcomes. The first step have K1 outcome, second step have K2 outcomes, and so forth, right? You have so many steps. But if you know the number of possible outcomes in each steps, okay, then what will be the total possible outcome for this whole experiment? You just multiply these numbers together, right? So that flip a coin and spin that wheel 2 times 4. This is like K1, this is K2, right? Casting 2 dice, this is like K1. First step, you have 6 outcomes. Second step, casting the second die, you have 6 outcomes. 6 times 6, you get 36, okay? So that's how we get this so-called fundamental principle of counting, okay? And we saw this example. If I want to choose 1 shirt out of the 3 that I have, and 2 jackets, 1 out of 2 jackets, and 1 pants out of 5 pants I have, okay? There are 3 steps. First, choosing a shirt. They have 3 ways. Second step, choosing a jacket. There are 2 ways to choose a jacket. And third step, selecting a pair of pants. I have 5 different ways to do that, right? So total, how many possible ways can I dress up myself, right? By picking a shirt and a jacket and the pants. There's 30 ways. Just multiply them together. Okay? I think that makes sense. So you from here, you identify all those K1, K2, K3, just multiply them together. Okay? This is assuming that you're doing random draw. You randomly select a shirt, or randomly select a jacket, right? Well, all these are possible to occur, right? Then if I say that, well, what's a chance if these three colors is yellow, maybe white, blue, and two jacket, yellow, white, blue, two jackets, one leather, one non-leather, okay, and 5 pens, maybe red, blue, white, brown, gray, whatever, right? What's the chance of getting a blue shirt, a leather jacket, and white pen? That's just one out of all the 30 possible ways, right? So if I randomly select one shirt, one jacket, and one pair of pants, the chance of getting blue shirts, leather jacket, and white pen, that's just one out of the 30 possible ways. So the chance of that is 1 out of 30. Okay? If you know how to count, then you'll be able to figure out the probability very quickly. All right? And we also talked about this so-called permutation problem. If I have this 4-letter base, B-A-S-E, I want to rearrange them to come up with different code words, 4-letter code words. How many different ways can I do that? Or how many different possible 4-letter code words that you can form, right? You can produce using these 4 letters by rearrange them. Okay, and we say that counting rule can be used too. I can separate into 4 steps, right? Since I have 4 letters to fill in, right? So the first step is filling the first letter. Since there are 4 letters to choose from, so I choose 1, right? But there are 4 letters to choose from. So the first step, I have 4 ways to do that. Second step, I'm going to fill in the second letter. Since I've chosen 1, I only have 3 other letters to choose from. So the second step, I have 3 ways to fill in that letter. And third step, I have 2 ways, and the last step, 1 way. So if I multiply them together, I get total 24 different ways, right? Or 24 different 4-letter code words that you can produce using these 4 letters by rearranging them. Okay? And this is called permutation. They have 24 total possible permutation of these 4 letters. Different arrangement I consider as different outcome. Does it make sense? And this can be done just by the counting principle, right? You don't really need a formula. But if you do need a formula, the formula is 4 factorial, okay? 4 times 3 times 2 times 1. Right? If you multiply a counting number from 1 up to a number 4, this number is called 4 factorial. Right? The definition of factorial, if you recall, the n factorial is 1 times 2 times 3 times 4, and up to this counting number n. This is called n factorial. What is 0 factorial? 0 factorial is defined to be 1. Okay? So that's a definition. So what is 3 factorial? 3 factorial is 1 times 2 times 3. That is 6. That's why I said, this is a 4 factorial because it is 1 times 2 times 3 times 4. That's 4 factorial. Okay. So what would be if you want to have a formula for this permutation problem, what would be the formula? Formula would be number of letters, right? Letters you have, and distinct letters, right? These 4 letters are all distinct, different from each other. Number of letters factorial. So here I have 4 letters. So 4 factorial is the answer, or the 4 factorial become the formula. If you like to have a formula. Of course, if you know the counting principle, you don't really need the formula, right? Just do it and consider you have 4 steps to go through, and you'll be able to solve the problem. Does it make sense? Okay. Now, how about this same letter can be used repeatedly? So I can have B, 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 right? Or A, 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 but just from these 4 different letters. So how many ways can I do that? Anybody? 4 times 4 times 4, right? Because for each letter, each letter, right, I have 4 choices, okay, for this 4-letter code words. Each letter, right, I can repeatedly use in the same letter, okay? So first step I have 4 ways, second step I have 4 ways, and third step I have 4 ways, and last step I have 4 ways. So 4 times 4 times 4, so it would be 4 to the 4th power. 256. So we have more possible 4-letter words, right, to form. Okay, good. How about I change the question a little bit? Totally, there are 26 letters, right, alphabet A through Z, and I want to choose 4 letters to form a 4-letter code words, and same letter cannot be used repeatedly. Then how many possible ways to do that? I can still use the counting principle. I separate into 4 steps. The first step, I'm going to assign a letter to it. How many different ways? There are 26 letters to choose from, right? So the first step is 26. Then the second step, fill in this second letter. Same letter cannot be used twice. So since I have used one, I only have 25 left. So this number of ways to perform the second step is 25. Okay. Then of course, then 24, and then 23. Okay. So this experiment involving these 4 steps. The first step at this many ways, second step at this many ways, and third step, and so forth. So I just multiply them together. I get the total number of possible ways that I can form 4-letter code words. Okay, and that same letter cannot be repeatedly used. Okay, does it make sense? All right, it's not too hard. If you know that counting principle, okay, this would be pretty simple to do. How about I can use the same letter repeatedly? Then that will be 26 times 26 times 26 times 26, right? That's 26 to the 4th power. That's, you get even more possible code words there. Okay. Now there is a formula called permutation formula. This is in case all these letters, all different letters. Okay. You have n different letters and you want to choose R of them and then form a code words. Okay. How many different ways can you do that? Or how many possible permutation? Okay. And notation-wise, people use like NPR. N denote total number of distinct objects or distinct letter. Like A through Z, there are 26, and then this N will be 26. If you're selecting 4 letters out of these 26 letters, this N will be 26. This R will be 4, right? You're selecting 4 distinct objects from these 24 objects. How many different ways can you form a 4-letter code word? And that's a permutation problem, because if you choose 4 letters, different arrangement of these 4 letters considers different outcomes. Okay, different permutation of the 4 letters consider different outcomes. So this is the formula for solving that problem. But we actually was able to solve it without the formula. What did we do for that 4-letter code words? Selecting 4 letters out of 26, I say it's 26 times 25 times 24 times 23, right? But sometimes people forgot that rule, but they do know that this is a permutation problem. And their formula that you can find, this is a permutation formula. What it does is that how this formula is defined is like total number of distinct object, n factorial, divided by n number of distinct object, subtract number of object you're selecting. Okay, this n is 26 for that alphabet problem. Okay, n is 26, this is 4. So you have a 26 factorial divided by 26 minus 4 factorial, which is 22. Okay, I wonder if you can relate it to this to the earlier problem. Let me grab a paper and show it to you how to relate this formula with the things that we just did. Okay. To solve this, taking 4 letters and form a 4-letter code words from the 26 different letters, okay? We say that the solution is 26 times 25 times 24 times 23. Okay, that was our answer. Total number of ways, right? 4 distinct letters out of 26 distinct letters to form a 4-letter code word. Okay, but that formula P, if you want to apply that formula, that is P26 4, right? You are selecting 4 out of the 26 distinct letters, right? And to see how many possible 4-letter code words. Applying the formula is n factorial. N is what? Totally 26 factorial. And divide by 26 minus 4 factorial. That's if you apply the formula. That's 26 factorial divided by 22 factorial, right? 24, 6, and 20 minus 4 is 22. Okay. Now this 26 factorial, if you know the definition, that is what? 26 times 25 times 24 times 23 times 22 times 21 and keep going. I'm going to just stop it here. I'd say it's 22 factorial. Does it make sense? Okay? And the denominator have 22 factorial. So this 22 and this 22 cancel. Isn't that just exactly the same as the answer we just got? Okay? It is that the mathematician realized that pattern. Okay? And they realized that you can use these information to actually come up with a formula. If you know total number of distinct objects, you also know how many distinct objects you're going to select to form a like 4-letter code words, right? Then you can just plug these information in the formula to solve the problem. The formula was what? The PNR is n factorial divided by n minus r factorial. Does it make sense? All right, so if you know the information, total number of distinct objects, you know this information, how many objects you're going to select, okay? And just plug this information in the formula, you solve the problem. That's doing it by formula. But again, you can do it without formula. You can do it using that counting rule to solve the problem, okay? Does it make sense? All right. So we have this permutation rules, but you don't really have to use it. If you know the counting principle, right, you can use it to solve the problem. And oftentimes people are confused with two formulas we're going to cover today, right? Permutation formula and combination formula. When we talk about permutation, it means what? If you rearrange these 4 letters, it is considered as a different outcome. Okay, that's permutation problem. Okay, let's look at more example. How many 4-digit code be formed by selecting 4 digits from 9 digits 1 through 9? Without repeating using the same digit, that means what? You're using 4 distinct digits, right? Isn't this exactly the same as the letters problem, right? It's just now become digit, but it's the same thing. Okay? Now if you apply that permutation formula, n is what? 9. N is total number of digits. There are 9 different digits. R is 4, since you're forming a 4-digit code. Okay? So you plug that in and use the formula. It's 9 factorial divided by 9 minus 4. And it is really just 9 factorial divided by 5 factorial, right? 9 minus 4 is 5. Then what you want to do is expand this 9 factorial to 9 times 8 times 7 times 6 and stop at the 5, because you know the 5 factorial and the denominator 5 factorial it can be eliminated, common factor, right? So it leaves you with the 9 times 8 times 7 times 6, which is 24. Again, you can do this with the counting principle. That the first digit, there are 9 choices. Second digit, you have 8, then 7 and 6. You can solve the problem, right? This is just additional things. You know, there's a formula if you prefer, right? You forgot your counting principle, but you do know that permutation problem. If you're dealing with permutation problem, there's a permutation formula for you to solve that problem. Okay, does it make sense? Okay, and it is important to understand this factorial, and you are able to expand this factorial, because the problem can be more complicated. What if I say I have 100 numbers, right? From 1 through, 100 symbol, not number, okay? 100 are all different symbols. I'm going to select 4 out of this 100 and form a 4-symbol code, okay? And it's going to be a problem if you try to figure out 100 factorial divided by 5 factorial, use your calculator, right? And you don't know how to expand this, because if you have a calculator, you can try whether you can calculate 100 factorial. Try it if you have a calculator. You have in your calculator, you may have a key that has an exclamation sign like this, okay? If you hit the number and then hit this factorial key, your calculator is going to return to you an error, because this number is so huge, okay? You can't do it with your calculator. So if that really happened, you got to know how to deal with this factorial, right? Be able to expand it and then do the cancellation, right, to solve the problem. Okay, calculator not always can do everything for you. Okay, so be careful, all right? Good. And I actually check out a lot of problems for you to practice from the chapter, right? You want to practice on these, okay? Okay, let's look at another situation. So we talked about permutation. When we talk about permutation, in fact, if you rearrange these digits, right, it's considered as different outcome. But if I change the question, I'm going to just select 4 digits out of those 9 digits. I don't care about how I arrange them. It's like a lottery game, right? If you have a lottery game, you just pick 6 numbers, and you don't care about how you arrange them. Just if you match these 6 numbers, you win the jackpot, right? That's very hard, though. Okay, so it's a combination of 6 numbers, and that's a combination problem. Okay, you don't worry about how do you arrange these distinct objects that you select. In that case, you have a combination formula. This notation looks pretty similar to permutation, except for here, this P becomes C. All right? If you are selecting R distinct objects from the N distinct objects, okay, you don't care about how you arrange them within these R objects. How many possible combinations, right, of R object that can be selected from N distinct object? The formula is N factorial divided by R factorial times N minus R. You notice that the difference is here. You add an R factorial in the denominator. Okay? If you don't have R factorial in the denominator, that's a formula for permutation. But why do we have an R factorial in the denominator? Well, because if you select R object, now that R object, there are R factorial that many possible permutation. Okay? But all these possible R factorial possible permutation is one combination. If you use a permutation formula, you're overcounting number of possible combinations because every R factorial of them is the same combination. That's why you divide by R factorial, and you get the formula for combination. Okay, let's see an example. Right? So in this situation, the order of these digits or numbers, right, doesn't matter. We don't worry about it. Right? Let's look at this example. How many ways can a committee be formed by selecting 3 people from a group of 10 candidates? You have 10 people. It's like you have 10 numbers, right? I'm going to select 3 numbers. How many different ways can I do that? Well, I cannot use like 10 times 9 times 8. I will have a problem because if I do that, I consider different arrangement of these 3 people as different outcome. Okay, so what I need to do is what? If I figure that out, I have to divide this. If I use a permutation formula, I got to count. I have to divide this number by 3 factorial because every 3 factorial of them is the same combination. All right? And so you have, if you use a combination formula, of course, if you use a formula, you first have to identify these numbers you need to use to apply the formula, right? How many total? In total, there are 10 candidates. How many are you selecting? 3. So you got an N and R. Simply just plug into the formula. N is 10, R is 3. Right? So this is 10 factorial divided by R factorial times this 10 minus 3 is 7 factorial. So you got this. Again, you can do the same thing. Expanding this 10 factorial is 10 times 8 times 9, and then stop at the 7 factorial so you can have 7 factorial and 7 factorial cancel. Okay? And now 3 factorial is simple. 3 factorial is 3 times 2 times 1. Right? So that's 6. So you have this 720 divided by 6, you have 120. And that's total number of possible combination of 3 people that you can select from 10 people. So this is different from the kind of question we did earlier. The kind of question we did earlier was about permutation. If you rearrange these people, okay, it considers different outcome. Right? I have Peter, John, and Paul. Right? If I rearrange, I have Peter first and Paul second and John third. That's considered different outcome. If that's the case, that's a permutation problem. But now I'm only interested in having a group of 3. I don't care about how I arrange within these 3. Right? That's a combination problem. Now you can use this formula, or if you know that multiplication principle, you can start from multiplication principle, and knowing that every R factorial is the same combination, so divide by R, you still can get the answer. Okay? But I guess, like when I'm doing this problem, I would just use a formula. I know that's a combination problem. I won't start from the counting principle and try to think through it and try to solve the problem. It'll take me more thinking, right? That's the reason we have formula. Okay? So to simplify these type of problems, usually what you want to do, right? Probably you can ignore the counting principle. It depends, right? Everybody have different thinking approach in solving problem. Okay? If you have trouble actually going through the thinking, right, the counting principle, and then divide by R factorial, then go ahead, just use this formula. It'll help you to solve the problem much faster. But before you use a formula, you have to pick the correct one. Are we dealing with a permutation problem, or are we dealing with a combination problem? Okay, let's see another example. How many ways can a combination of 4 digits be selected from 9 digits? It's a combination of, so this is much closer to a lottery game, right? But you have 9 digits, you want to choose 4 digits. Now again, I don't care about how I arrange them. I arrange these 4 digits. How many ways can I do it? To do this problem, first of all, I have to figure out what is n, what is r. So I can plug those numbers into the formula to solve the problem. N is what? 9. I totally have 9 different digits. And r is 4. I'm going to select 4 distinct digits. Okay? So with that, I just plug those numbers into the formula. This n is 9, r is 4. Okay? So it's 9 factorial divided by 4 factorial times 9 minus 4 factorial. And then, of course, 9 minus 4 is 5. Okay? Then what I would do is, again, expand this 9 factorial to 9 times 8 times 7 times 6 and stop at 5 factorial. So 5 and 5 factorial, they cancel. They're a common factor. And 4 factorial is 4 times 3 times 2 times 1. Okay, so you know that. Now, when you reach here, you should be able to solve the problem. It's 126, right? Just a division. Or if you want to simplify it further, this is 2 and 3 is 6 and cross out 6. And this is 4 and 8, so cross out 4 and you have a 2 here. 2 times 7 times 9, right? Depends on how you want to do it. Some of you probably prefer using a calculator to finish it, right? But that's fine. Okay. But the point is, can you reach here to get the answer? And again, this is a combination. You just want a 4-digit. You don't care how you form this 4-digit. You are not forming a 4-digit code word. Okay? So the combination formula is good. Make sense? Does it make sense? Okay. Now this is kind of more closer to a lottery game. We have 47 digits. I don't know why a lottery game may have more. Anybody know? Anybody play? Even probably not. Okay. Well, that's a good decision, right? Because the expected value, which we will talk about it later, the expected value for that kind of game is negative to you, so that they can raise money for some education or other purpose. Okay. But anyway, if the game is set up this way, right? You have 47 distinct numbers. Maybe start from 0 to 46, or maybe from 1 to 47. Anyway, you have 47 distinct numbers, and you can pick 6. Okay? Now, how many possible ways can you do this? How many possible ways can you pick 6, right, out of 46 number? Again, that's a combination of permutation problem. Which one? Is it combination or permutation? Combination, right? You don't care about how you arrange these 6 letters, right? So first you identify n is 47 and r is 6 and just plug them into the formula, right? N is 47, r is 6. So you get this. And again, you want to expand this 47 and stop at 41, right? So 41 and 41 cancel, and then that will help you to simplify the problem. I wonder if your calculator can handle 47 factorial or not, right? You probably don't want to do that. You want to expand this a little bit and simplify it, okay? So the number outcome is what? It's 10 million, more than 10 million. That's what's 47 digits. I think Ohio Lottery game had more than 50, right? So it's really way higher than this 10 million possible outcome. Winning the jackpot is 1 out of those 10 million, 10 million. Okay, in probability term, we call this almost 0, right? The chance of winning jackpot is almost 0. But there's still some people winning, right? There's got to be some people, right? So anyway. So what's the chance of winning jackpot? Jackpot is 1 out of those 10 million, right? So it's 1 out of those 10,737,573. Okay, and that's a chance of winning it. Okay, so you can calculate this probability, right? People ask you in the future. Years ago, we have several actually people in this area won the jackpot from Giant Eagle store, actually twice from Giant Eagle store. And local news reporter come to me, ask me, what happened, why? Just explain to them using this. No, it's chance, right? The chance of that is small, but sometime it happened, okay? So anyway, this lady keep asking me to get this number for him so she can report it, right? But I guess everybody finish a college degree, you have some stat course, you should be able to calculate, right? If you forgot it, just go back to your stat textbook, or you'll be able to find it, how to get it. Okay, good. Now, remember I mentioned the birthday problem? If I have 23 people in a group, the chance of at least 2 of them having same birthday is about like flipping a coin, getting a head turns up. It's about like that. It's pretty high. Most of us say it's less than 10%, but it's not. Okay. Now to solve it, you can use this counting technique. Assuming I have 23 people, how do I find out what's the chance of at least 2 people having the same birthday? Well, this is what you're looking for, at least 2 people having the same birthday. Now, if you try to solve it directly, it's very hard. You want to find 2 people having the same birthday, 3 people, or 2 groups, of 2. Well, there are so many possible situations. It's going to be hard for you to solve, right? So how do we solve that then? Using that complementation rule. All right, this is one application of complementation rule. What's a complement of at least 2 people having the same birthday? That's nobody have the same birthday, right? You cannot find any match, right? So if you have 1 minus nobody have the same birthday, everybody have the same different birthday, right? 1 minus that would be the probability of these 2 people having the same birthday. Okay, that will help us to simplify the problem, all right, the way to solve the problem. Otherwise, there are so many possible situations out there. If you can find the probability of each of those and add them together, that's good, but that's just too time-consuming. Do you see how I can solve it with this complementation rule, right? This is a complement of this. At least 2 people having same birthday. What's a complement of that? Everybody has different birthday, okay? How do you figure out what's the chance of everybody have different birthday? First of all, you have to count how many ways, all right, you can assign birthday so that everybody has different birthday. Divide by total number of possible ways that you can assign birthday to these 23 people. Am I making sense? All right? If you know how many ways you can assign birthday to these 23 people, you also know how many ways can you assign birthday to these 23 people so that nobody have the same birthday. The ratio of that is the probability of nobody have the same birthday. Right? Let me do it and put it here, okay? This is how many ways you can assign birthday to these 23 people so no one have the same birthday. How do we do that? We can separate into 23 steps, right? First step, assign the birthday for the first person. There are 365. I'm assuming that a year there are 365 days, okay? Then the second step is what? Assign the birthday for the second person so that second person won't have the same birthday as the first one. You only have 364 ways. Then 363 ways, and so forth. You have 23 terms, okay? Multiply them together, that's how many ways you can assign birthday to these 23 people so that no one have the same birthday. Am I making sense? Okay? Now, this 365 to the 23rd is total number of ways you can assign birthday to everybody. You can have everybody have the same birthday, okay? Or 2 people have the same birthday, or 3 people have the same birthday. So in this situation, or the 23 step, each step you have 365 ways. Okay, so that's 365 raised to the 23rd power. So this is the size of the sample space, right? Sample space. And this is number outcome in the event. Nobody have the same birthday. Ratio of that give you the probability of no one have the same birthday. 1 subtract that. Oops, sorry, I didn't give you the answer. 1 subtract that. You can use your calculator. 1 subtract that. Give you a number that's almost 0.5. That means almost 50%. Okay, we have actually probably around 20 students in the class. I wonder, have I ever shown you whether, did I ask you to enter a birthday? I think I did, right? And did we do a survey in this class? We did not in the beginning? So maybe I would check on that to see whether we have a match, right? Every semester I did that, I had a match. Either 1 pair or 2 pairs that have the same birthday. Okay. A lot of times students don't believe it. One-time student, I didn't ask people to do that. A one-time student circulating a paper in the class. And before she did that, she said, I want to bet with you. I want to bet that, $5 that no one will have the same birthday. I only have less than 20 students in the class. After the paper all circulated and everybody put down their birthday, there's 1 pair that has the same birthday. She wanted to pay me that $5. I said, no, forget about it. But anyway, sometimes, your intuition doesn't work quite right? But if you have these basic knowledge of probability, you can calculate and to really figure out what's the chance of those to occur. Let me give you a few other things to think about, right? You should have this also on the web, but let's look at this. How many ways can 5-letter and word think be arranged to form a new 5-letter code words? if I ask you to do this, first of all, is this a permutation or a combination problem? Permutation, right? Why it's permutation? Because if you rearrange them, right, it's a different outcome, right? So what's the answer to this then? Yeah, 5 times 4 times 3 times 2 times 1. That's 5 factorial, right? If you have 5 distinct objects, the number of permutation for this 5 distinct objects is 5 factorial. If you have n distinct objects, the number of permutation for these n distinct objects is n factorial. Okay, but you can use the counting principle to get this. Okay, good. So that's 5 factorial, right? 1 times 2 times 3 times 4 times 5. How about this? If one wishes to randomly select a representative from a group of 20 individuals, what's the probability, including Paul, what's the probability that Paul will be selected? This is probably, you don't even need to use a permutation or combination. This is a simple ratio. 1 out of 20, that's right? Okay? Anybody, the chance of anybody to be selected, right, in that is, right, anyone, right, is 1 out of 20 because totally are 20 people. Okay? Makes sense, good. How about this one? There are 5 male students and 8 female students. How many ways can one select 2 students, 1 male and 1 female? So you're forming a committee. And this committee has to have a male and have a female. There are 5 male and 8 female. How many ways can you form this committee?
40.
Yeah, okay. How do you do that? It's like you have 2 steps. The first step is select the male, and second step is selecting the female, right? Now, how many ways can you select the male? You have 5 male students, so there are 5 ways to do that. How many ways can you select the female? There are 8 different females, right? So there are 8 ways to choose that, right? So your 2 steps, there are 5 ways first step, 8 ways second step, 5 times 8. Okay, or you can list them and give each one a name or number, right? So 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2. Use a tree diagram, you can figure that out too, right? But you can use that, if you understand the counting principle, counting rules, right, then this will be pretty simple, okay? Or you draw a tree diagram. You forgot your counting principle, draw a tree diagram, so that'll help. Okay, good. Now this will be a little bit more complicated. Still 5 males and 8 female. How many ways can you form a committee so that there are 2 male and 3 female students? This one combine counting principle and other formula. If you know the formula, right, for the combination formula, in fact, right, you can solve this. Care to try it? I'll give you 30 seconds. See if you can figure out how this can be done. You can separate into 2 steps too. First step is selecting those 2 male. Second step is selecting those 3 males so that you can have that committee of 5. Okay. So your first step, how many ways? And your second step, how many ways? If you know that, then you're almost done. Anybody has an answer to this? This is how you do it. Right? Did you do it this way? There are 2 steps. First step is selecting those 2 male. Since there are 5 male in total, right? How many ways can you select 2 male out of those 5? That's combination of 5 takes 2. The second step is selecting those 3 female. There are totally 8 female students, and you want to select 3 so that there are this many ways. Okay? And if you can multiply them together, that's total number of ways to select these committee, right? 2 male and female to form this committee. Now, how do you calculate that? That's 5 factorial over 2 factorial times 3 factorial, right? That combination formula. How do you calculate this? That is 8 factorial divided by 3 factorial over 5 factorial, right? And so what I did is I expand this to 5 times 4 times 3 factorial so I can cancel the 3 factorial. Expand this 8 factorial, 8 times 7 times 6 times 5 factorial, stop at 5 factorial, so this can be canceled. I can actually cancel further. 2 and 3 is a 6, right? 2 and 4. So this is actually what? 560. Anybody get this? 560? Okay. Some of you got it. Okay. So when I solve this problem, usually I would just use a formula. I won't start from counting principle. Okay. I know that it's a combination problem, so I just go ahead and use a combination formula to help me to get number of ways I can select 2 out of 5 or 3 out of 8. Does it make sense? Everybody follow? Okay. I think these problem also is on the WebCT, right? And, yeah, if you see those, okay. And also there are answers in that page too, so you can look up that, right, from WebCT. So let's look at another one then. We have a few minutes. How many ways can a person select 3 different books from a bookshelf that has 10 different books? Basically, just select 3 different books out of 10 different books. Okay. How many ways can you do that? Is that a combination or permutation problem? Combination. You care just there are 10 books. No matter it's in the bookshelf, in the book bag, whatever, right? There are 10 books. You want to select 3, so that's a combination of 10 takes 3, right? Or yeah, it says 10C3. Can you apply that formula? Right. Good. How many ways can you select 3 pictures from a collection of 5 pictures and hang them on the wall in a row, right? So when you arrange these pictures in different ways, that consider different outcome. So how many ways can you select 3 pictures and hang it on the wall? How many different arrangement? Or how many different permutation now, right? Because if I arrange the picture in a different order, that considers different outcome. So in this case, it will be 5p3. Right? Permutation of 5 takes 3. Okay? Good. If you plan a trip to visit 4 countries, how many can, from 10 countries, you want to choose 4 out of 10 countries, how many different ways can you, choose these 4 countries? Is that a permutation or combination problem? Combination. Okay, but usually, if you really plan a trip, there is like which country is your first stop and which country is the second stop and so forth. You do care about which one country goes first, right? So you're making plans. How many different plans can you choose so that the different arrangement of these country or order, right, of the country that you visit counts as different outcome. In that case, this is that permutation problem. So this is 10p4, right? Then you use that formula, you can solve the problem. Yes. Yeah, a different order considers a different outcome. Although you have same 4 countries, but if you arrange differently, that's considered a different outcome. That's permutation. Okay? If you don't care how I arrange them, it's all one combination. That's combination problem. Okay? But you have to practice though, right? I think you get the idea. You just have to practice more. Okay? Good. Any question? No questions? Okay, good. Good day.